So let's see if this thing is working. Yes, it is. I have a bit of an issue here because during the lunch break, I met two persons, and one was pushing more towards a general presentation, and the second one was pushing more towards a technical presentation. So let's see how juggling between the two comes up. First of all, thanks very much, Dimitra and Rob, for the invitation. I'm very happy to be here. I'll try to take you through a journey of what happened in the past 5 to 10 years in single-photon detectors, positron emission tomography, hype or truth, breakthroughs, or more of the usual stuff. So the group I'm working in has been active in single-photon imaging applications for quite a while. And here you see a snapshot of the developments that we have tackled over the past 13, 14 years or so, ranging from 3D vision to near-infrared imaging, quantum security, biomedical applications, and last but absolutely not least, time-of-flight positron emission tomography. And that's what I'm going to concentrate in the following. Given that it's after lunch, I skip the outline and I go immediately to a short PET refresher. So for the specialists in the audience, you can sleep now. For the other ones, just keep in mind a couple of acronyms that I'll be using all over the place. SPAD, which stands for Single-Photon Avalanche Diode. That is a pixel-sensitive single photons implemented mostly in the standard CMOS technologies. And a superset of it, a silicon photomultiplier that is gradually replacing traditional photomultipliers. What is PET all about? Well, we have seen that it provides functional information. Patient is administered with radio tracers, and it's nowadays combined with either CT or MR information, which provides structural information. The images that you get at the end of the day, I like the ones that are shown here. How do we get up to this point? Let's try to see, and let's try to build bottom-up a PET scanner and its different elements. The patient is basically surrounded by one or more rings of detectors that you see here. What these detectors do is the following. The radio tracer that is injected in the patient, which in most cases is a fluorideoxyglucose, a sugar analog, emits a positron, which is an anti-electron that travels a short path around a millimeter until it annihilates, and then E equal mc squared. The whole energy is transformed into two gamma rays that shoot off in exactly opposite direction, back to back, of unique and precise energy, 511 kilo electron volts. And these gamma rays need to be detected in coincidence because they are emitted at the same time. And when this is done, they define a line of response along which the event that we're looking at has been located. So the event is part of a set of events that happen, for example, in a tumor, because the tracer accumulates there. What we want at the detector level and then system level is information on the time of these events, their energy, and their position in order to reconstruct the global image. What you see on the bottom left is an image from the GE Discovery IQ of one of these detector blocks seen from the outside that is seen from the scintillating crystals. Now let's have a look at one of these blocks to understand how they work. In most cases, like it was illustrated previously for X-rays, the detection is done in an indirect way. The gamma photon impinges on a scintillating crystal, which can be either a monolithic block or, in most situations, still nowadays, an array of needles that funnel the light that is generated within this scintillation block towards a photosensor that is located at the bottom in a standard geometry. Typically, we have some tens of thousands of photons per scintillation, and then we detect a few thousands of them. So with this information that is concentrated in a short time, about 200 nanoseconds, we have to obtain x, y, point of impact, sorry, the origin of the event, the pulse arrival time, and the pulse energy. So if we go then to the photosensor itself, in most of the systems, up to a few years ago, the photosensors was a photomultiplier tube. This is good old technology that has been around for decades. Basically, you convert the visible light photons via photocathode into electrons that are then amplified down a chain of elements called diodes via high voltages. And at the end of the day, you have a macroscopic current at the exit, and that's what you detect and analyze. About 30 years ago, the concept of a silicon photomultiplier was proposed. This is basically an analog solid-state equivalent of the photomultiplier, if I simplify to the extreme. You have to imagine it as starting from a technology which is similar to the one that you have in your cell phones, which is a CMOS technology for the experts. And eventually, what the manufacturers have been able to do over the years is to come up with larger and larger sizes and better specifications for these detectors. So what you see here, for example, is an array from Sencell that is a few tenths of square centimeters in size. And that is gradually replacing the photomultiplier tubes that we have seen on the top. A simple previous generation clinical PET system is, for example, built like this. If you have a look at the internals, in this case, it was a PET ring of 24 modules. The axial field of view, that is the length, is about this much, so 15 to 20 centimeters. The transaxial field of view, somewhere between 50 and 70 centimeters. And if we have, again, a more detailed look into one of these blocks, seen from the back this time and not from the front, what we basically see is an array of photomultipliers, which are these elements here, that see the scintillating crystal, which is on the back, through a light guide. So the light from a scintillation event is spread over a number of photomultipliers. Recording the signals from all of them allows you to determine the information that I mentioned before. In this case, the needles for a clinical system are around 3 to 4 millimeters in size, times about 20 millimeters in length. If we want to explore the world of preclinical systems, so systems of much smaller size that are used, for example, for imaging of small animals, then the needles that actually you see here in the background, this is an image, a zoomed-in image of a scintillating array, are much smaller because you want a much higher spatial resolution. In this case, they are about 1 square millimeters, and they're also much shorter, about 13 millimeters in this case. The detectors used here are an advanced version of the photomultipliers called position-sensitive photomultipliers that provide additional positional information at a cost, obviously. The previous speakers have briefly introduced the concept of time of flight. So in a nutshell, what it is all about. If you don't have any accurate timing information, you don't know exactly where your event was along the line of response. If you start going into the nanosecond timing resolution, remember the rule of thumb, 1 nanosecond is 30 centimeters of free path in air. Then you start getting in an area where you can basically shrink down the point in which your reconstruction algorithm thinks that the event took place. And if you go towards 500-600 picoseconds, then it gets really interesting. And these are previous generation clinical systems, like the one mentioned by the previous speaker. If you then can shrink it down further towards 300 picoseconds, or even towards the 10 picosecond barrier that we are going to see at the end, then all the better. The quality of your image increases, and the signal-to-noise ratio is basically increasing as 1 over the timing resolution. So far, so good. Now, why do we want to replace photomultipliers, which, after all, have a number of pros? They don't cost that much. It's a mature technology, et cetera, et cetera. Well, one of the key arguments was, in combination with a magnetic resonance with an MR system, the fact that you cannot use them in magnetic fields. So the whole thing breaks down, basically. The silicon photomultipliers, on the other hand, are highly tolerant to magnetic fields. They have a very high sensitivity, very high timing resolution of the order of tens to hundreds of picoseconds that makes them perfectly suitable for time of flight. The spatial granularity, that is the density of points that you can measure in space, can also be very high. One of the disadvantages up to some time ago was cost. But this is also gradually coming down. Now, maybe the experts can switch on again. And we're going to have a look very briefly at some of the fundamentals of this new generation of detectors, single-photon avalanche diodes. From the electronic engineering perspective, an avalanche photodiode is a restricted area, restricted volume in space, in an electronic chip, where the electric field can be so high that impact ionization can result. This means that if you have a visible light photon that creates an electron-hole pair, then this electron-hole pair can be separated and amplified so as to generate a macroscopic current. And this can be achieved nowadays in a repetitive manner. There is a difference between a standard avalanche photodiode and a single-photon avalanche photodiode. If you go into the IV plot, which means we plot the current that flows through the device versus the applied voltage, in a standard avalanche photodiode, we work in this regime, which is kind of linear. Whereas in a so-called Geiger mode single-photon avalanche diode, we work beyond the breakdown voltage. This might seem impossible because if it's called breakdown, it has a reason. But actually, these devices can operate in that regime for very short periods of time. And by doing this, they can achieve a virtually infinite gain. So very high amplification of the optical signal. The trick is, and I will not go into further details here, is that once they are operating here and they generate an event, you have to bring them back here in order to quench the avalanche that has been produced. And you repeat this process over and over again for each detection. What are the key parameters of these single-photon avalanche diode sensors? Well, the first parameter that is of particular importance in time-of-flight PET is the timing resolution, which can be extremely good, tens to hundreds of picoseconds. The sensitivity has also seen a quite important decrease these past 5 to 10 years. Well, first of all, when we speak of photon detection probability, because not each photon actually generates an event. So some of them are not detected. But this probability can easily reach 50% nowadays. We also speak of field factor, because not all the whole area of this 10 or whatever square micron, or hundreds of square microns, is photosensitive. It's only a part. But this fraction has also been steadily improving. One of the, say, perhaps downsides is that each of these devices has a dead time. So a time during which, after one detection, it cannot detect another photon. And this is of the order of 10 to 100 nanoseconds, which, if you remember one of the previous slides, is exactly of the order of the scintillation. So what this means in practice is that you cannot use a single SPAD to detect a scintillation event, because you would detect the first photon, and then the whole thing would be dead. So you somehow need to oversample, either spatially or temporally. For example, having a look at one scintillation event with hundreds of thousands of SPADs instead of a single one. There is also a noise, which for these detectors is called a dark count. so that even in the dark, these devices trigger at the level of hundreds or thousands of events per second per SPAD, which means that if you scale this to a macroscopic surface, you would have millions of, you do have millions of dark counts. Now, you can still use these devices because the scintillation event is concentrated in time. And therefore, on the time scale of a scintillation event, the noise can be made negligible, or the detector can be made robust to noise. Just one plot, two plots actually, on the sensitivity in terms of photon detection efficiency. This is an older plot from Philips, from one of the Philips sensors. You have here on the vertical scale the photon detection efficiency, and on the horizontal scale the wavelength of the impinging photons. 400 to 800 is about the visible range. Here you are in the blue, and down here you are in the red. The nice thing is that these devices are peaked at around 400, 450 nanometers, which is exactly the wavelength peak of the emission in one of the main scintillators that is used nowadays, lutetium orthosilicate. So it's very nice that these two things are well arranged. You can also see that other scintillators that are faster, like titanium bromide, have their peak in the near ultraviolet. So for these, you would need to change a bit your detectors. This is a similar image obtained by the SPADNet project that we are going to see later on. Also a peak around in that area, 400, 450. Now, how do I go from a single SPAD pixel? Let's see. Opla, here it is. That is something like this, a few tens of micrometers in scale on each side, and with a sensitive area here in the middle, to an array of these devices, and then eventually to a system like illustrated here in the background, taking in mind, for example, that in a clinical PET machine, I need to cover an area with silicon that is about half a square meter. Well, broadly speaking, I have, very broadly speaking, sorry to the experts, I have two approaches, analog versus digital. In an analog approach, I take each of the sensors, so each circle here is a diode, which is a single detector, and I sum up the signals into one single current, macroscopic current, that I then analyze and detect. This means that I don't have any additional information, for example, within an array of pixels where the photons have impinged. In a digital approach, I can do another thing. I can take the output of each of these pixels, create a digital signal that says, yes, there has been a photon, no, there has been none, or implement in silicon miniature chronometers that are called time-to-digital converters that time the arrival of each photon. So at the extreme, I could even do this for each of the thousands of photons in a scintillation event. If we look a bit, this is the first slide on this subject, so that's why I numbered it 0. There will be a couple of other ones at the end about the advantages and disadvantages of these two approaches. In the first approach that we saw, the analog one, I can really optimize the performance of the silicon photon avalanche diodes, of my photosensors. On the other hand, I need to couple them with readout electronics, and this needs a careful design. In the other approach, in the digital one, I can integrate, at least in theory, everything in a single chip. So I can have the photodiodes here and ancillary processing electronics in an area of the chip, but on one and the same substrate. In principle, having access to devising smart architectures that can give more information on the single event. And we will see later systems that have been built with either one or the other of these approaches. So if you go to state-of-the-art clinical spot-based systems, the first one, which is actually based on Avalanche photodiodes, is the biograph, or the Siemens MMR biograph that you have shown and that came onto the market a few years ago, and which was the first truly integrated solid-state PET and MR system. This is a block of scintillating crystals sitting on top of a matrix of detectors, the ancillary electronics here, and then this is where it is located within the actual bore of the magnet, so sandwiched between the RF coil, the body coil here, and the other main coils on the edge. And so, okay, I'm not going to further details here. Philips has started developing this kind of detectors in a sort of submarine mode, so without telling anybody anything, about 10 years ago. And then they went public in 2009, 2010. They have gone for a number of generations of their digital photon counter. And then they have released this system, the Vereos, about a couple of years ago. In this case, they have so this is a clinical-based system. I don't know, to be frank, how many of these have been sold. They have coupled the crystals one-to-one to the pixels of their digital detector. They have opted for perhaps a bit limited axial field of view of 16 centimeters, 4 millimeter resolution, and perhaps what's most important, they have a resolving time, coincidence time of 325 picoseconds. And this is an exploded view of one of their sensor modules, where perhaps the part of interest to us is the photosensor tile itself, and then the scintillating array that is placed on top of it. Last but not least, the GE Signa, which is, again, an integrated PET-MR solution, but using, to the best of my knowledge, pixelated analog SIPMs, so one of the other approaches that we mentioned, in a free Tesla magnet, with a relatively long axial field of view of about 25 centimeters, and relatively long scintillating crystals as well of 25 millimeters to increase the overall system sensitivity. So the longer the crystals, the more event you capture into the crystals themselves, with a timing resolution that is, again, below 400 picoseconds, so definitely quite good. And I believe that their PET-only system has been certified recently or FDA approved, so I guess that we are going to see it on the market soon. Now, if I have a look now at a couple of R&D projects with which I have been in closer contact. One of them is PADNet. So it was a European project started 5 years ago, where we use as foundry ST microelectronics. The idea here was to do a digital system, relying a lot on the concept of a networked photonic module. The background is really sensor networks, where each element in the network acts as a processing and sensing node and communication node. This is a schematic overview of one of the elements, well, that I can actually show you right now, so that you have an idea how it looks like. This is 5 by 5 by 5 centimeters. And let me just jump back so that it looks a bit less abstract. Scintillator, quite standard. This is the so-called sensor tile, so it's an array of sensors, like the one that we have seen before. And on the back of it, we have a field programmable gate array, so an electronic module that can do frontline computation. It can do first computation inside the photonic module itself, for example, localized processing, in situ noise filtering, and which can then take this process data and transmit it to the nearest neighbors for a first analysis. The underlying concept is that you try to do as much processing in the module itself as you can in order not to overload the network, in order to have a system with higher scalability, and that ideally only data which is of interest to the processing, to the reconstruction computer gets to it. This is a picture of a second generation 5x5 module with scintillating crystals on top. So again, the front part is the sensing, and the back part is basically the computation and the communication. This is a schematic of how we conceived the sensor network in a cylindrical mesh topology. Each of these points here, of these circles, is one of the 5x5 centimeter blocks that you have seen before. And the idea is that once one of these sensor modules has detected an event, it calculates its time of arrival and injects that information into the ring, where it propagates in the ring itself and in the other rings. So actually, so that all other modules are aware of this information and they can determine if they have seen an event in coincidence. If that's the case, then both modules process the event fully and transmit the resulting full coordinates to an outside computer for reconstruction. If that's not the case, and that happens in quite a few situations where you only detect one of the photons and the other one has gone lost or has been scattered, then that information is not retained and you save bandwidth, basically. This is a photomicrograph of the first spotnet sensor chip that was developed, 5 by 10 millimeters, with quite high granularity. So each pixel here was a 600 micron in size. If the idea that you could put any size of needle on top of it, whether small or whether large. This is a micrograph of the individual SPADs, the silicon-photon avalanche diodes. So our photon detectors, round in this case. And here you see the detector once manufactured from the front and from the back with the ball grid array that enables then assembly on a host PCB. The second generation system was also designed and is under characterization. Size is twice as much as the first one. There have been improvements in the shape of the individual sensors, the fill factor, etc. What is more interesting, you actually see here in the background the individual SPADs, which have been made square here in order to increase the amount of photosensitive area. Is that in the periphery we have built in smart electronics, let's say, and that's one of the advantages of these CMOS approaches, to do tasks like on-chip event centroiding. It means calculating the XY coordinate of the point of impact directly on chip, or frame buffering in order to decouple the readout from data transmission. So basically you can transmit data while the chip is still collecting statistics. Which were some of the challenges specific to this project? Well, there was an engineering challenge. This is building a totally new digital SIPM, which is an effort more or less equivalent to what Philips has done over 8 years. Life cycles, design cycles, let's say, in these digital processes are more demanding than in analog processes, and costs are also not small, because you need to design, you need to pay for a mask set for those in the trade. There's a general question about the market. So if we follow a paradigm of standard CMOS, the only way of decreasing costs here is to producing these things in quantities, in volume, like happens a bit with smartphone electronics. Is there a sufficiently large market to drive costs down here? Even if a single PET machine consumes half a square meter of silicon, which is not bad, is there a market overall? The second concept that I wanted to illustrate is completely different and goes into endoscopic. So an endoscopic PET approach. forget the traditional ring of standard PET machines. In this case, the driving idea was to put on the tip of a standard ultrasonic endoscope a single detector of size 2 by a bit less than 1 centimeters, and to couple it with an external plate. Everything time of flight enable, about 200 picosecond timing accuracy. The two target scenarios were pancreas, that is still a highly lethal disease, unfortunately, and prostate. And in particular, the pancreas was challenging because of the very tight space and volume that you have on the tip of a standard endoscope that then needs to go in the body and travel until its destination close to the pancreas itself. I'll illustrate just one component here that is a multi-channel digital SIPM that was designed in Delft by Eduardo Charbon and his colleagues there. So given that this system uses only a single detector or maybe two side by side, what you can do is that you can put your photosensitive area here, and you can use you put your intelligence basically outside of the photosensitive area. In this case, the team eventually opted for a 9 by 18 array of single multi-channel digital SIPMs, and in total a bank of 432 time-to-digital converters. One of the reasons to have that many timestamps is that there's a theory or the statistics that tells you that if you get a timestamp of the first or the second photon of the event, that's not necessarily the best choice that you can do. If you have 10, 20, 40 photons available, you can use, you can go to much higher precision. This is a photomicrograph of the sensor itself, so 20 by 7.6 square millimeters. This is a single pixel. Sorry, it's not very readable here. 800 times 800 microns, basically, which was quite small because the idea was to couple it with a fiber, extremely fine fiber of the same pitch, 800 microns, so very high spatial accuracy. And this is a couple of SPAD back to back of size about 50 times 30 micron, so relatively large. Again, you have to imagine, well, we will actually see it. Yes, we will see it. You have to imagine a scintillating block on top of the detector. You don't see the individual fibers or crystals here, but each of them acts like a light funnel and brings the light to the sensitive surface itself. So we see here the back PCB that does also the computation. And I think that was one of the most challenging parts, how to do a system that is as compact as this one in the limited volume. You see here the assembled system. And this is an early prototype. So this is the ultrasonic part of the endoscope. This is the detector itself, with the system that is actually undergoing commissioning and as soon as it's ready, preclinical tests. A few scintillation events. So this is the sensor itself, 20 millimeters by 7.6, with an array of scintillating crystals or fibers on top. This is a single scintillation event, and this is a so-called flood map. So it's an image of accumulated statistics over some time, where you see all the individual needles and also the spatial granularity of this type of the detector. And this is similar, but a bit larger size, or actually double that much, a single scintillation event. So what was challenging here? Well, it was certainly the engineering. This is, again, a totally new sensor developed within an academic background, so using master and PhD students. High granularity, real-time data processing on the field programmable gate array. This is indeed quite challenging. How can I fit into that small computational space and volume all the algorithmics that is needed not to saturate the network. Miniaturization, that I think we also mentioned. At the general level, there is obviously a system cost versus benefit question here that might be more tolerable given that we are in a research project. But at the end of the day, if you want to manufacture this, then someone is going to ask, yes, but how much will it cost? What will it bring? And probably the killer question, which are the available radio tracers, both for prostate and for pancreas. So for prostate, I think that there are a few that are coming up. Pancreas is really, really challenging. Need for close ties to system manufacturers. In this case, it's also the manufacturers of the endoscope. Most of them happen to be on the other side of the planet, and that doesn't make things easier. So if you now expand your horizon and forget about the complexity of bringing things to the market for a second, apologies for this stretch. When I first heard of this, then I thought these guys are completely crazy. But someone has set up a kind of informal challenge. What if we could go for a timing accuracy of 10 picoseconds? So if you remember the rule of thumb, which is 30 centimeters per nanosecond, so this is 3 millimeters. And this is something that would bring your reconstruction accuracy in the range of the physical limitation of the positron. So the positron actually does not annihilate immediately. Once it's emitted, it scatters a bit, but it scatters for something like a millimeter. Some say that this would be equivalent to direct imaging without reconstruction. And although life is probably not that easy, that's still something that would greatly improve your final outcome. So how far are we from this barrier? This is data from IEEE NSS of a month ago, where CERN folks have put on, they have used a small scintillating cube, 2 by 2 by 3 millimeters, which is a bit cheating because if the crystal is so small, then light propagation is very short. So it's not the same thing as in a long crystal, but still. And they have put it onto a series of commercially available silicon photomultipliers from Hamamatsu, Ketek, Sencel, FPK, etc. And they have reached timing resolutions that are below 100 picoseconds, which I would probably have been unthinkable 10 years ago, I guess. Now, again, this needs to be translated then to system level, from which we are quite far. But the bunches of projects out there that are pushing really the different aspects of the problems involved here, also the electronics, towards such resolutions. Okay, this is another thing when where I had exactly the same reaction as before. So what do these guys want to do? It turns out that if you enter into a scintillating material with a charged particle whose speed is larger than the speed of light in the medium, in that specific medium, you generate so-called Cherenkov photons that have a completely different wavelength distribution, so they are more in the blue, but they are generated promptly, so immediately. And this would greatly increase your detection, or your timing accuracy, sorry. The problem is that you don't generate that much of them, let's say 20, something like that, at least for the materials that have been studied so far. So this calls for photodetectors with high sensitivity in the blue, etc. And again, there are a few groups that are working on that. Interesting thing, quite lately, it has been shown that these are also produced in the good old BGO, germanium, bismuth, etc., that was used as scintillating material in previous generation PET machines, but was then abandoned because of its long scintillation tail. So apparently it was impossible to time of flight with that thing, and now it's coming back from the rear window. And another approach on which Eduardo is working within the Polis project and the Sherbrooke University has a great group is to go for what I would term the ultimate photon sensor. It's basically coming back to what I showed you before between when you're discussing analog versus digital systems. What if you had a time-to-digital detector, so a chronometer, for each single pixel? You would basically be able to measure the whole photon field with extreme accuracy. And there are some 3D integration techniques, like pioneered by big foundries for also commercial cell phone developments, etc., that are pushing the ways in which a photosensor array can be stacked with an underlying array of detectors. Don't ask me about the cost of this, but as long as we are talking research, then we can even do this thing, NIH $15 million. Okay, when I heard this, I still had the same reaction, so maybe it's me who is a bit biased, but yes, indeed, Simon Cherry has been able to push things forward on this front. What happens if I have a real full-body system? How is my sensitivity increasing, not only from the timing resolution or from the improvement of detector efficiency perspective, but from the fact that I have a perfect solid angle coverage. And what he sees, what his vision is for this, is that you would be able to image better because your signal-to-noise ratio would obviously increase, or you would image faster, a total body scan in 5 seconds, that would not be bad, or maybe image longer, in the sense longer after having been injected with a radiopharmaceutical, or what he calls image gently, so with great reduction in dose that might open up new populations like pediatrics to this kind of applications, and maybe for screening as well. Okay, so it's time to summarize and then conclude. I'll go back to this slide, analog versus digital, a bit enhanced with some of the elements that we learned along the way. Yes, analog, you can obtain optimal SPAD performance. You can use a fully sensitive area. Maybe here, with this integrated approach, you can profit from the intelligence that you put on chip. What is true is that what the technology that you use here is not always optimized for what you want to do. So there might be a compromise there to be taken. However, with this approach, you could build something that is close to the ultimate photon detector, a bit exaggerating, obviously. One thing that you can also do is if you have a detector here that is noisy, you can in principle turn it off. Because all the elements here are individually addressable, whereas in a single-photon multiplier, you add everything together. So if you have something there that is not working properly, you will find it at the output. Okay, power consumption, yes, that's probably one thing that is underestimated. And the development time that you need in order to program all this thing. So, some final considerations. Dramatic improvement in silicon photomultipliers in the past 5 to 10 years. This is really amazing when you go each year at NSS and the major producers present results that are really improving. We did not go here into the details of possible hybrid approaches. What if I take an analog system and I couple it directly with a field programmable gate array? Maybe I don't need any readout electronics anymore. We mentioned volume as one possible issue. One of the things that always strikes me is that there's a lack of a Lego type approach. If you as a team want to design a new SPAD, then you basically need to do it. It's hard to go to a foundry and tell them, but can you give one to me so that I embed it in a system that I'm designing? Industry wants volume, yes, but for example, ST Microelectronics, with which we collaborated, which has taken over the technology developments, has learned to do SPAD, and they are now selling a miniature sensor that I can show to you later, to doing some easy time-of-flight ranging for the autofocus of the phones in your smartphones. And they have been able to sell tens of millions of these. So in that case, the volume was found. But it's absolutely not the same sensor that you're going to sell here. And it's a bit also what Philips was trying to do at a certain point in time. They were trying to see which other applications they could be selling into. But that's not easy. Just a word of thanks to the Aqua groups in Switzerland, the Netherlands, the European projects that I mentioned, so SPADNet and Endoscopic PET, and a list of contributors from which I stole some material here and there. Thank you.